Hello students. So our today's topic is on point of contraflexures under SFD and BMD. This is probably the last topic that I'm going to cover from that uh, topic SFD BMD. So what's point of contraflexures? So point of contraflexure is a point on the BMD, that is point on bending moment diagram, where bending moment is used to change its sign, or rather you can say where bending moment is equal to 0. Both mean same. And the same point, if it being projected on the beam, it's being termed as point of inflection. So the point on the bending moment diagram is being termed as point of contraflexures, and the same point, if it is being projected on the beam, it's being termed as point of inflection. So this particular topic, the point of contraflexure, is not required for simple cantilever beam. This topic, you are getting the use of that topic only when you are solving the problems either from simply supported beam or rather the overhanging beam. So we are trying to understand the topic point of contraflexure by choosing a problem. So now we have chosen a problem which is not yet being shown to you. It's a problem from overhanging beam, as the beam is A, B, C, D as it's shown, and it's being supported at two positions, point A and point C, where there is a UDL in between A to B, and there is a point load at the extreme end, point D. So the distance on me mentions in A to B is 4 meter, B to C is 4, and C to D is 2. First, we are trying to solve the problem by moving through the steps. As you know, I have already told you in the earlier videos. So step 1 is finding support reactions. So there is RA and RC moving in the upward direction. So RA plus RC is equal to 20 into 4, as there is a UDL, plus 30 for this. So it's 110 by summation of VF, that is vertical force, equal to 0. And the next equation comes from summation of moment equal to 0 as RC into 8. So it's used to move in this direction, that means used to move in the anti-clockwise directions, but the other is used to move in the clockwise direction, which is to point A. So by choosing the moment at A equal to 0, we can make that equation as equation number 2, and from there we used to find out the first value of the RC, and putting the value of RC in equation number 1, we can get the value of RA, as RC will come as 57.5 and RA will come as 52.5. And as I told you earlier, as always keep the space below of this figure remain blank, so that you can be able to put the SFD and BMD just below of the drawn or given figure. So here we can write the values as RC come is equal to this and RA equal to come as this. Now we move to step 2. First, draw the corresponding sign conventions, as you know. So now we are trying to find out the shear force at each of the points. So FA, here we are going to look it from left side of the beam. So if you want to calculate the F at A, you should put your hand like this. Now see, you can see from the left hand side. Can you see from the left hand side? Yeah. So there is a force FA moving in the upward directions. So upward from left is positive, so it will be plus 52.5 as the value of RA. FB similarly, FC you can do that. Now finally we are finding as there is a point C, and we know there is a note, as if there is any intermediate point load acting on a loaded beam, you have to calculate the initial and the final. As like that, there is a point load, intermediate point load at point C. So we used to calculate FC initial once and then FC final. And finally we used to calculate the FD. Who know the procedure has how to calculate, I have shown it earlier. Move to step 2, and there we have find out this. In that figure, then you can see there is a point where shear force is used to change its sign, and this point is very vital because as we know the slope of the bending moment is totally depends on the shear force, and the bending moment is maximum where shear force is 0 or change its sign. So here you can see in the diagram shear force is used to change its sign in two positions, one is at point C and this is at point P. So we have to find out the location of point P, so that we used to take help of this particular triangular diagram. After getting this value, first place the SFD, then you can see at point P the shear force is used to change its sign from plus to minus, and here is shear force equal to 0. Now we have to find out the point P, and we can do that by the so to find point P where SFD is equal to 0, we use the similar triangle concept, as a triangle is one triangle is AFAP, another is BABP. From there we can do as S divided by this is equal to 4 minus S, because this total is 4. So if this is S, this will be 4 minus S divided by that. So we know the values. By putting this, we can find out S equal to 2.625. And after knowing this S equal to 2.625, we can be able to find out the moment at that point also. Now move to step 3. So try to find out the bending moment. Before that, first try to draw the sign conventions. As we know, this is plus, this is minus. So here, by applying this, we can find out the moment at A, moment at B, moment at C. I'm just indicate one moment, that is moment at C, suppose. So moment at C, if we want to calculate the moment over here, that point, we can write moment at C equal to this force multiplied by that distance, moving in that direction, clockwise, looking from left. So looking from left hand side, it's indicate. So MC to be plus this moment. But what about that moment? It's moving the clockwise from left, so it will be minus. So 20 into 4 plus this distance 6. If you want to calculate for C, then this distance is 4, clear, B to C. But what about the acting point? It will be 4 by 2. That's why 4 plus 4 by 2, like this. Similarly, moment at D. And finally, we used to calculate the moment at P also. And it comes as 68 point. The highest moment come at point P. After getting all these values, we can place the corresponding moment diagram. Here it will be a parabola, look like this. And here the maximum value comes at moment at P. That's why, and again there's a drop and finally it comes to 0 and then move in the linear directions. You can see as it's written there, as there is 2 points, one is point P and another is point C, where shear force is 0. And at that time, you can see in the bending moment diagram, we are getting the maximum value moment as well as the minimum value moment. So wherever shear force is 0, you should find the corresponding moment value either the maximum or the minimum. Now the next is, you have drawn that particular diagram. Now the next point is point Q. So what is point Q? Where bending moment is used to change its sign. And that point Q is being termed as point of contraflexure. So we can find out the point Q, the location of point Q, as moment at that point is equal to 0. It's visible. So we can write the corresponding moment equation. If you look from left, it will 52.5 into, come here, 52.5 into 4 plus this distance. If you choose this distance x from B, so you can write 52.5 into 4 plus x. That will be positive because it tries to move in the clockwise, minus this part 20 into 4, the total force moving acting from this. So what should the distance from Q? It will be 2 plus x. So 2 plus x. By doing that, we can find out the value of x will come as 1.818 meter. This x is being chosen from point B as it indicated here. So from left support, if we want to calculate from support A or point A, then Q star, that means the point of inflection, the same point which is located on the point of beam. So Q is termed as point of contraflexure, whereas this Q star can be termed as point of inflections. So from left support point A, Q star is located at a distance of 4, this 4 plus 1.81 meter, this x equal to 5.81 meter. So that is the end of this whole topic SFD and BMD. So what you have to do, try to practice some more problems considering the different types of beams and try to practice some problems including the topic point of contraflexure also. So that is end, that is from end, that is today's end. So thank you, and that's all.